right now, at this very second, somewhere in the universe, a star is dying. Not the gentle fading of a candle flame, not the slow cooling of embers in a fireplace. Now, this is violent. This is catastrophic. A star 25 times heavier than our sun has just run out of fuel, and gravity, the most patient force in the cosmos, has finally won. The core collapses in milliseconds. The outer layers explode outward in a supernova brighter than an entire galaxy. But the core keeps falling. It falls past the point where atoms can hold their shape, past the point where even neutrons can resist. It falls and falls and falls until something extraordinary happens. The matter compresses into a region so small, so unimaginably dense, that space-time itself warps beyond recognition. Light, the fastest thing in the universe, tries to escape and fails. A black hole is born. Now here is where things get interesting. Imagine you are holding a book, a thick, beautiful book, filled with stories, equations, histories, poems. Every letter on every page represents information. The arrangement of atoms in the ink, the structure of the paper fibers, the binding, the cover, all of it is information. Now imagine you throw that book into this newly formed black hole. The book crosses a boundary called the event horizon, a point of no return, and vanishes from the observable universe. Gone, every word, every letter, every atom. But here is the question that will drive this entire journey. Is that information truly gone? Has the universe permanently erased something? Or does nature have a rule, a deep, unbreakable law that says information can never be destroyed? This single question, this deceptively simple puzzle, ignited one of the longest, most bitter, and most profound scientific debates in the history of physics. It pitted Stephen Hawking against Leonard Susskind. It divided Nobel Prize winners. It spawned public bets, dramatic concessions, and shocking reversals. It forced physicists to question whether our universe might be a hologram, whether space-time itself is an illusion, and whether the very fabric of reality is woven from something called quantum information. This is the black hole information paradox. And today, we are going to explore every single angle of it. From the moment it was born in the mind of Stephen Hawking in 1974, to the latest breakthrough calculations in 2019 and beyond that may finally be cracking the code. We are going deep. We are going thorough. And I promise you, by the end of this journey, you will never look at the universe the same way again. Before we dive in, if you love deep explorations of the biggest mysteries in physics, subscribe to this channel and hit that notification bell. Drop a comment right now telling me what you think happens to information inside a black hole. Does it vanish forever? Does it somehow escape? Or is it trapped in some form we cannot yet imagine? I genuinely want to know what you think before we begin, because by the end of this video, you might change your mind completely. Now let us start at the very beginning. And by the beginning, I do not mean black holes. I mean something even more fundamental. I mean information itself. When physicists talk about information, they do not mean the evening news. They do not mean data on a hard drive or words in a textbook. In physics, information has a very precise meaning, and understanding it is absolutely essential to grasping why the information paradox matters so deeply. At its core, information in physics is about distinguishability. It is about the ability to tell one thing apart from another. If you have two objects that look identical from the outside, a red ball and a blue ball for instance, the color is information. It tells you which ball is which. Now extend this to the quantum level. Every particle in the universe has a quantum state. An electron has spin, position, momentum, energy. A photon has polarization, frequency, direction. These properties define the particle's state, and that state is the information. In classical physics, the physics of Newton and everyday life, information is deeply tied to the concept of determinism. If you know the exact position and velocity of every single particle in a system at one moment in time, you can, in principle, calculate where every particle will be at any future moment. You can also calculate where every particle was at any past moment. The equations work both ways, forward and backward. This means nothing is ever truly lost. The information about the initial setup of the system is always preserved in its later configuration, even if it gets incredibly scrambled and spread out. Think about it this way. Imagine you have a glass of water and you drop a single drop of red ink into it. At first, you can see the drop clearly. Then it starts to spread. After a few minutes, the water is uniformly pink. The drop of ink seems to have disappeared. But has the information about that original drop been destroyed? Not at all. If you could somehow track every single molecule of ink and every single molecule of water, you could, in principle, reverse all their motions and reconstruct the original drop. The information is still there. It has just been scrambled beyond any practical ability to recover it. But in principle, it survives. This idea, this principle that information is never truly lost, was so deeply embedded in classical physics that most scientists never even thought about it explicitly. It was just assumed. It was part of the furniture of physics, so fundamental that nobody questioned it. Then came quantum mechanics in the early 20th century, and everything got much stranger, but also, in a profound way, much more precise about information. In quantum mechanics, the state of any system is described by something called a wave function. This wave function contains all the information about the system. It tells you the probability of every possible measurement outcome. The wave function evolves over time according to a mathematical equation called the Schrödinger equation. And this evolution has a very special property. It is governed by what physicists call a unitary operator. Now, unitarity. This is a word you are going to hear many times in this journey, so let me explain it carefully. Unitary evolution means that the process is reversible and information preserving. If you know the final state of a quantum system, you can always, in principle, figure out what the initial state was. The mathematical machinery of quantum mechanics guarantees this. No information leaks out. No information is created from nothing. No information is destroyed. The total information content of a closed system remains constant. There is a beautiful way to think about this. Imagine a cosmic jigsaw puzzle. At the beginning, the puzzle is assembled, showing a clear picture. As time passes, the pieces get shuffled and scrambled. The picture becomes unrecognizable. But here is the key. No pieces are ever removed from the box, and no new pieces are ever added. Every single piece is always there. In principle, you can always reassemble the puzzle and recover the original picture. That is unitarity. That is the conservation of information in quantum mechanics. And this is not some optional feature. This is not a nice property that physicists would prefer to be true. Unitarity is load-bearing. It is structural. If unitarity breaks down, quantum mechanics itself becomes mathematically inconsistent. Probabilities stop adding up to 1, which means they stop being probabilities. the entire framework collapses. You cannot have quantum mechanics without unitarity any more than you can have arithmetic without the number 0. There is one more quantum mechanical principle that will be absolutely crucial later in our story. It is called the no-cloning theorem, and it says something remarkably simple and yet profoundly important. You cannot make a perfect copy of an unknown quantum state. If you have a particle in some quantum state and you try to duplicate it to create a second particle in exactly the same state, quantum mechanics forbids it. Information in the quantum world cannot be copied. It can be moved, it can be transformed, it can be scrambled, but it cannot be duplicated. So let us take stock. Classical physics says information is never lost. Quantum mechanics says information is never lost, and never copied. These are bedrock principles. They are the foundation upon which all of modern physics is built. They have been tested in countless experiments and never been found wanting. And now let me tell you what makes the black hole information paradox so devastating. It appears to show that black holes violate these principles, that somewhere in the life and death of a black hole, information is destroyed. And if that is true, then either quantum mechanics is wrong or our understanding of gravity is wrong, or both. Either way, something fundamental about reality needs to be rethought. But I am getting ahead of myself. Before we can understand the paradox, we need to understand black holes. Not the cartoon version. Not the science fiction version. The real thing, as described by Einstein's general theory of relativity. Let me take you back to 1915. Albert Einstein, after 8 years of grueling mathematical struggle, publishes his general theory of relativity. It is one of the supreme achievements of the human intellect. In this theory, gravity is not a force in the traditional sense. It is not some invisible hand pulling objects toward each other. Instead, gravity is the curvature of space-time itself. Space-time is the 4-dimensional fabric of the universe, 3 dimensions of space plus 1 dimension of time, woven together into a single entity. Mass and energy tells space-time how to curve, and curved space-time tells objects how to move. A planet orbits a star not because an invisible rope is pulling it, but because the star's mass curves the space-time around it, and the planet follows the straightest possible path through that curved landscape. Now, just a few months after Einstein published his theory, a German physicist and astronomer named Karl Schwarzschild did something remarkable. Serving on the Russian front during World War I, in the trenches, Schwarzschild found the first exact solution to Einstein's field equations. He solved them for the case of a perfectly spherical, non-rotating mass. And in his solution, he found something strange. If you compressed a mass below a certain critical radius, now called the Schwarzschild radius, something bizarre happened. There was a boundary in space-time where the curvature became so extreme that nothing, not even light, could escape from inside it. At the time, nobody quite knew what to make of this. Einstein himself did not believe such objects could actually exist in nature. He thought the mathematical solution was just an artifact, a curiosity that had no physical relevance. Schwarzschild died shortly after his discovery, from a disease he contracted in the trenches. His solution sat in the literature, regarded by most as a mathematical oddity. But nature, as it turns out, does not care about human opinions. Over the following decades, other physicists gradually clarified the physics of Schwarzschild's solution. In 1939, Robert Oppenheimer and Hartland Snyder showed theoretically that a sufficiently massive star, having exhausted its nuclear fuel, could indeed collapse under its own gravity to form such an object. In 1958, David Finkelstein clarified the nature of the Schwarzschild radius, showing that it was not a physical barrier, but a one-way membrane in space-time, a surface of no return. You could cross it going inward, but you could never cross it going outward. In 1963, Roy Kerr found the solution for rotating black holes, which is far more realistic since all stars spin. In 1964, the term black hole had not yet been coined. It was John Archibald Wheeler, the great American physicist, who popularized the name in 1967. Black holes. Objects so gravitationally extreme that they swallow everything, even light. Now let me describe a black hole in more detail, because the details matter enormously for our story. A black hole has two key features. The first is the event horizon. This is the boundary I mentioned, the point of no return. It is not a physical surface. There is no wall, no barrier, no solid edge. It is a region of space-time defined purely by the geometry of gravity. If you were falling toward a black hole, you would notice absolutely nothing special as you crossed the event horizon. The space around you would look perfectly normal. You would not see a sign saying, "Warning, you are now entering a black hole." You would simply be in a region of space-time from which escape is no longer possible. There is a wonderful analogy for this. Imagine you are in a canoe on a wide, calm river. But this river has a waterfall ahead. As you paddle downstream, the current gets stronger and stronger. At some point, you cross an invisible line where the current is too strong for you to paddle against. You cannot turn back. But when you crossed that line, nothing visible happened. The water looked the same. The air felt the same. You only realize you have crossed the point of no return when you try to go back and discover you cannot. That is exactly what the event horizon of a black hole is like. The second key feature is the singularity. This is the center of the black hole, at least in the non-rotating case. At the singularity, all the mass that formed the black hole and all the mass that has subsequently fallen in is compressed into a single point of theoretically infinite density. Space-time curvature becomes infinite. The laws of general relativity, which describe the rest of the black hole perfectly well, break down completely at the singularity. They produce meaningless infinities. This is a signal, a flashing red light, telling us that general relativity is incomplete. At the singularity, we need a more complete theory, a theory of quantum gravity that merges general relativity with quantum mechanics. And as of today, we do not have such a theory in its complete form. Now, there is a crucial idea about black holes that was formulated in the early 1970s, and it has a colorful name. It is called the no-hair theorem. John Wheeler is credited with the catchy phrase, "Black holes have no hair." What this means is profoundly important. A black hole is completely described by just three numbers: its mass, how heavy it is, its electric charge, and its angular momentum, how fast it is spinning. That is it, three numbers, nothing else. Think about what this means. Imagine two black holes with exactly the same mass, charge, and spin. One was formed from the collapse of a massive star made primarily of hydrogen and helium. The other was formed from a hypothetical star made entirely of iron. From the outside, these two black holes are absolutely identical. You cannot tell them apart. There is no measurement you can make from outside the event horizon that will reveal what the black hole was made of, how it formed, or what has fallen into it since. All the complexity, all the rich detail of the matter that formed the black hole, every atom, every quantum state. Every bit of information has been hidden behind the event horizon. The black hole has forgotten everything about its origins except those 3 numbers. Now, does that disturb you? It should. Because we just spent a long time establishing that information cannot be destroyed. We said that the arrangement of atoms in a system always contains recoverable information about the past. But a black hole seems to erase all of that. A library and a ball of gas, if they have the same total mass, produce identical black holes. The information about which one it was seems to have vanished. This was the first warning sign. The first hint that something deep and troubling was lurking in the relationship between gravity and information. But in the early 1970s, most physicists were not alarmed. They assumed the information was still inside the black hole, locked away behind the event horizon. It was not destroyed, just inaccessible, like a book locked in a safe. You cannot read it, but the words are still there. That assumption was about to be challenged in the most dramatic way imaginable. But first, we need to meet a remarkable young physicist named Jacob Bekenstein. In 1972, Bekenstein was a graduate student at Princeton University, studying under John Wheeler himself. And Bekenstein had an idea that would change physics forever. The story begins with a thought experiment about thermodynamics. Thermodynamics is the branch of physics that deals with heat, energy, and entropy. And entropy is a concept we need to understand carefully. Entropy, in the broadest sense, is a measure of disorder or randomness. More precisely, it counts the number of microscopic configurations that are consistent with the macroscopic properties you observe. Consider a room full of air. The air molecules are zooming around in every direction. You can measure the temperature and pressure of the air. These are macroscopic properties. But there are trillions upon trillions of different ways the individual molecules could be arranged and still give you the same temperature and pressure. The entropy counts those arrangements. High entropy means many possible arrangements. Low entropy means few. The second law of thermodynamics is one of the most fundamental laws in all of physics. It states that the total entropy of a closed system never decreases. Things naturally evolve from order to disorder, from low entropy to high entropy. An egg can break, but a broken egg does not spontaneously reassemble. Hot coffee cools down, but cold coffee does not spontaneously heat up. The second law gives time its direction. It is the arrow of time. Now here is the problem that troubled Bekenstein. Suppose you have a box of hot gas. It has high entropy. Now, you throw that box into a black hole. The gas vanishes behind the event horizon. From the perspective of the outside universe, the entropy of that gas has disappeared. The total entropy of the observable universe has decreased. But that violates the second law of thermodynamics. You might say, well, the entropy is still inside the black hole. But remember the no-hair theorem. The black hole has no features that could represent entropy. It is completely described by mass, charge, and spin. Where is the entropy? Bekenstein's bold proposal was this. The black hole itself has entropy. And the entropy of a black hole is proportional not to its volume, as you might expect, but to the area of its event horizon. This was a stunning claim. Entropy proportional to area, not volume? For every other physical system in the universe, entropy is proportional to volume. A room twice as large can hold twice as many states. But Bekenstein was saying that for a black hole, the information content is captured by the surface, not the interior. Bekenstein even proposed a precise formula. The entropy of a black hole is equal to the area of its event horizon divided by 4 times the square of the Planck length, all multiplied by Boltzmann's constant. The Planck length is an incredibly tiny distance, about 10 to the power of -35 meters. It is the scale at which quantum gravity effects become important. When Bekenstein first proposed this, the reaction from the physics community was mixed at best. Many were skeptical. Stephen Hawking, who was already one of the most prominent figures in gravitational physics, was initially hostile to the idea. Hawking had recently proved a beautiful theorem showing that the area of a black hole's event horizon can never decrease. This was called the area theorem, and it was analogous to the second law of thermodynamics, which says entropy can never decrease. But Hawking considered this analogy to be just that, an analogy, a mathematical similarity without physical substance. Hawking's reasoning was straightforward. If a black hole has entropy, then by the laws of thermodynamics, it must also have a temperature, and if it has a temperature, it must radiate. But nothing can escape a black hole. Therefore, a black hole has 0 temperature and, strictly speaking, no entropy. The analogy with thermodynamics was merely formal, Hawking argued, not physical. This seems like a strong argument. If nothing can escape, there can be no radiation, no temperature, no true thermodynamic entropy. Case closed. Or so Hawking thought. What happened next is one of the most beautiful twists in the history of science. Hawking set out to prove Bekenstein wrong and ended up proving him right. And in the process, Hawking discovered something that would create the greatest paradox in modern physics. It was 1974. Stephen Hawking, by then confined to a wheelchair and communicating with increasing difficulty due to motor neuron disease, turned his formidable intellect to a new calculation. He wanted to understand what happens when you apply the principles of quantum field theory to the environment around a black hole. Let me explain what that means. General relativity describes gravity and the structure of space-time. Quantum field theory describes all the other forces and particles. Normally, these two theories operate in separate domains. General relativity governs the very large, galaxies, stars, black holes. Quantum field theory governs the very small, atoms, electrons, quarks. But near a black hole, you have an unusual situation. The gravitational field is extremely strong, and the spacetime is highly curved, but you still have quantum fields existing in that curved spacetime. Hawking's idea was to study the behavior of quantum fields in the curved spacetime near a black hole's event horizon, while treating the spacetime itself classically, according to Einstein's equations. This hybrid approach is called semi-classical gravity. To understand Hawking's discovery, we need to talk about the quantum vacuum. In quantum field theory, empty space is not truly empty. It is a seething, restless sea of activity. The uncertainty principle, one of the foundational principles of quantum mechanics, dictates that you can never have a quantum field that is precisely zero everywhere. There are always fluctuations, tiny random variations in the field's value. These fluctuations are sometimes described, somewhat loosely, as virtual particle-antiparticle pairs constantly popping into existence and annihilating each other too quickly to be directly observed. Now, near the event horizon of a black hole, these quantum fluctuations encounter an extreme gravitational environment. Hawking's calculation showed that the curvature of spacetime near the horizon has a remarkable effect. It can promote these virtual fluctuations into real observable particles. Specifically, the intense gravitational field separates the fluctuations in such a way that one component falls into the black hole while the other escapes to infinity as a real particle. From the perspective of a distant observer, the black hole appears to be emitting a steady stream of particles. It is glowing. It is radiating. This radiation came to be known as Hawking radiation, and it is one of the most profound theoretical discoveries of the 20th century. But let me be more precise about what is happening, because the virtual particle picture, while intuitive, is somewhat misleading. A more accurate description involves the concept of what different observers consider to be empty space. In quantum field theory, the definition of a particle depends on the observer. An observer freely falling into the black hole would define particles and vacuum differently from an observer hovering far away. Hawking showed that what the freely falling observer considers to be empty space, the distant observer interprets as a thermal bath of particles. The black hole is radiating simply because different observers disagree about what empty means, and the curvature of space-time near the horizon mediates this disagreement. This is related to a phenomenon called the Unruh effect, discovered independently by William Unruh, which shows that an accelerating observer in flat spacetime perceives the vacuum as filled with thermal radiation. The connection is not accidental. An observer hovering just above a black hole's event horizon must accelerate enormously to avoid falling in, and the radiation they see is intimately related to the Unruh effect. Now, here is the truly stunning part. Hawking calculated the precise temperature of this radiation, and the result is elegant and beautiful. The temperature of a black hole is given by a formula involving Planck's constant from quantum mechanics, the speed of light from relativity, Newton's gravitational constant from gravity, and Boltzmann's constant from thermodynamics. It is the only formula in physics that simultaneously involves all four of these fundamental constants from different branches of physics. It stands at the crossroads of quantum mechanics, gravity, and thermodynamics, a hint that these seemingly separate domains are deeply connected. The formula tells us that the temperature is inversely proportional to the mass of the black hole. This means bigger black holes are colder and smaller black holes are hotter. A black hole with the mass of our Sun would have a temperature of about 60 billionths of a degree above absolute zero. That is incredibly cold, far colder than the cosmic microwave background radiation that fills the universe at about 2.7 degrees above absolute zero. Such a black hole would absorb far more energy from the cosmic microwave background than it would emit through Hawking radiation. It would actually grow over time, not shrink. But imagine a very small black hole, perhaps one created in the early universe. Such a black hole could be very hot. And here is where things get dramatic. As a black hole radiates, it loses energy. Losing energy means losing mass, since energy and mass are equivalent by Einstein's famous equation. Losing mass makes the black hole smaller, and a smaller black hole is hotter. A hotter black hole radiates faster. Radiating faster means losing mass faster. Losing mass faster means getting even smaller and even hotter. Do you see what is happening? It is a runaway process. The black hole radiates, shrinks, heats up, radiates more, shrinks more, heats up more, radiates even more. The process accelerates without bound. In its final moments, the black hole is unimaginably hot, radiating in a catastrophic final burst, and then, poof, it is gone. The black hole has evaporated. Let me give you some numbers to appreciate the timescales involved. A black hole with the mass of our Sun would take approximately 10 to the power of 67 years to evaporate. That is a 1 followed by 67 zeros. For reference, the current age of the universe is about 14 billion years, or roughly 10 to the power of 10 years. So a solar mass black hole will last for an incomprehensibly long time. But a black hole with the mass of a large mountain, about 1 billion tons, would evaporate in roughly the current age of the universe. And a black hole with the mass of a small car would explode in a tiny fraction of a second. The point is clear. Black holes are not eternal. They have a beginning, a middle, and an end. They are born from collapsing matter. They live for an immense duration, radiating faintly, and they die in a final explosive burst of Hawking radiation. They are, in a very real sense, mortal. Hawking's discovery vindicated Bekenstein in a spectacular way. Black holes do have temperature. They do radiate. And therefore, Bekenstein was right that they have genuine thermodynamic entropy. Hawking himself refined the entropy formula, completing the proportionality constant that Bekenstein had not been able to determine. The Bekenstein-Hawking entropy formula is now one of the cornerstones of theoretical physics. But Hawking's discovery came with a devastating price. It created the information paradox. Here is the problem, and I want you to feel it, to really understand why this is so troubling. Hawking showed that the radiation emitted by a black hole has a very specific character. It is thermal. This means it has the same statistical properties as the glow from a hot oven or a heated iron bar. A thermal spectrum is the most random, most featureless type of radiation possible. It is characterized by a single number, the temperature. It carries no other information whatsoever. Think about what this means. Two black holes of the same mass, one formed from the collapse of a star and the other formed from the collapse of a vast cloud of books, would emit exactly the same Hawking radiation. The radiation from the star black hole would be indistinguishable from the radiation from the book black hole. Every quantum state, every bit of information about what fell in, appears to be completely absent from the radiation coming out. Now follow the logic to its devastating conclusion. A black hole forms from matter in a specific quantum state, a pure state in the language of quantum mechanics. This state contains complete information about the matter that formed the black hole. The black hole then slowly evaporates, emitting Hawking radiation that is purely thermal and carries no information about the original matter. Eventually, the black hole evaporates completely. Nothing remains except the Hawking radiation, which is featureless thermal noise. Where did the information go? There are only a few logical possibilities. Either the information escaped in the Hawking radiation, but Hawking's calculation says the radiation is thermal and carries no information. Or the information is still inside the black hole, but the black hole has completely evaporated, so there is no inside anymore. Or the information was truly destroyed, erased from the universe permanently. If the information was destroyed, then the evolution from the initial pure state to the final thermal state is not unitary. It is not reversible. You cannot reconstruct the initial state from the final state. Unitarity, the bedrock of quantum mechanics, is violated. Hawking himself embraced this conclusion. In a landmark 1976 paper, he argued explicitly that black holes cause a fundamental breakdown in the predictability of physics. He proposed that the evolution of quantum states in the presence of black holes is described not by unitary evolution, but by a different mathematical framework, one in which information is genuinely lost. He was, in effect, saying that quantum mechanics, as we know it, is incomplete. That the existence of black holes forces us to modify the most successful theory in the history of science. This was not a minor technical quibble. This was a frontal assault on the foundations of physics. And it divided the physics community in a way that few scientific disputes ever have. On one side stood Hawking and a number of general relativists who took the result at face value. Black holes destroy information. Quantum mechanics needs to be extended or modified to accommodate this fact. The classical structure of space-time, with its event horizons and causal boundaries, is telling us something profound, that information loss is a real feature of the universe. On the other side stood a growing group of physicists, primarily from the particle physics and string theory communities, who refused to accept information loss. They argued that unitarity is non-negotiable. If Hawking's calculation predicts information loss, then Hawking's calculation must be wrong, or at least incomplete. Somehow, some way, the information must escape. The challenge was to figure out how. This debate would rage for nearly 50 years. It would produce some of the most creative, audacious, and beautiful ideas in the history of theoretical physics, and it is far from fully resolved even today. Let me now walk you through the paradox one more time, very carefully, because I want you to appreciate just how tightly the trap is constructed. There are 3 principles involved, each of which seems rock solid, and yet they cannot all be true simultaneously. Principle 1. Quantum mechanics is correct, and unitarity holds. Information is never destroyed. The evolution of any closed quantum system is reversible. This principle is supported by every experiment ever conducted in quantum physics. There is no known violation of unitarity, not even a hint of one. Principle 2. General relativity correctly describes the large-scale structure of black holes. Event horizons exist. The region inside the event horizon is causally disconnected from the outside, meaning nothing inside can influence or communicate with anything outside. The singularity is shielded from the external universe. Principle 3. Hawking's semi-classical calculation is valid in its domain of applicability. The radiation emitted by a black hole is thermal to a very good approximation, at least until the black hole becomes very small and quantum gravity effects presumably take over. If all 3 are true, then information is lost, because the radiation is thermal and carries no information. The information cannot escape, and yet it must survive. Contradiction. To resolve the paradox, at least one of these 3 principles must be wrong or must be modified in some significant way. But which one? And how? This is what makes the information paradox so extraordinarily deep. It is not a problem within any single theory. It is a conflict between theories. It sits at the intersection of quantum mechanics, general relativity, and thermodynamics, 3 pillars of physics that are individually among the most well-tested and successful theories ever developed. The paradox forces them to clash, and in their clash, it reveals that our understanding of nature is incomplete. Now, let me paint the picture of the human drama that unfolded around this scientific crisis, because science is not done by equations alone. It is done by people, with egos and intuitions and passions and blind spots. In 1983, at a physics conference in San Francisco, Stephen Hawking presented his argument for information loss to an audience that included a young American physicist named Leonard Susskind. Susskind, a brilliant and outspoken theorist at Stanford University, was deeply disturbed by what he heard. He later described the experience in vivid terms. He felt as though the foundations of physics were being threatened, as though something terribly wrong was happening, and almost nobody in the audience seemed to realize it. Susskind was convinced that Hawking was wrong. Not because he had a specific counterargument, but because his physical intuition told him that information loss would be catastrophic for physics. If information could be destroyed by black holes, the consequences would ripple outward and undermine the consistency of quantum mechanics everywhere, not just near black holes. This intuition was eventually formalized. Several physicists, including Tom Banks, showed that if you modify quantum mechanics to allow information loss, you inevitably break other things too. Energy conservation gets violated, or the theory becomes non-local in uncontrollable ways, or the vacuum becomes unstable. Pulling out the brick of unitarity causes the entire wall to collapse. Gerard 't Hooft, the Dutch Nobel laureate, felt the same way as Susskind. He was independently convinced that information must be preserved and began developing his own ideas about how this might work. And so the battle lines were drawn. On one side, Hawking and the gravitational physics community, arguing that black holes destroy information and quantum mechanics must be modified. On the other side, Susskind, 't Hooft, and a growing cohort of particle physicists and string theorists, arguing that information is preserved and general relativity must be modified near black holes. Leonard Susskind would later write a book about this decades-long intellectual struggle titled The Black Hole War. He was careful to note that it was a war of ideas, not personalities. The participants remained friends and colleagues throughout. But the stakes were enormous. The outcome would determine the direction of fundamental physics for generations. Let me now introduce you to the first major proposed resolution, an idea that emerged from the work of Susskind and his collaborators in the early 1990s. It is called Black Hole Complementarity, and it is one of the most creative and counterintuitive ideas in all of physics. The inspiration came from quantum mechanics itself, specifically from the principle of complementarity first articulated by Niels Bohr. Bohr argued that in quantum mechanics, certain properties are complementary, meaning they cannot be observed simultaneously. Light is both a wave and a particle, but you can only see one aspect at a time. The wave nature and the particle nature are complementary descriptions that together give the full picture. But they never conflict because they cannot be measured in the same experiment. Susskind, along with his collaborators Lars Thorlacius and John Uglum, proposed something analogous for black holes. They suggested that the information is both inside the black hole and outside it, encoded in the Hawking radiation. But there is no paradox, because no single observer can ever verify both descriptions simultaneously. Here is how it works. Consider two observers. Alice stays outside the black hole, far away, and watches the evaporation process. Bob falls into the black hole. From Alice's perspective, as she watches from a safe distance, things unfold like this. She sees matter falling toward the black hole and approaching the event horizon. But due to the extreme gravitational time dilation near the horizon, she never actually sees anything cross it. Instead, the infalling matter appears to slow down, flatten out, and spread across the event horizon like a thin film. To Alice, the information in the infalling matter accumulates on the horizon, in a thin layer called the stretched horizon. This information is then gradually released in the Hawking radiation, encoded in subtle correlations between the emitted particles. From Alice's perspective, no information is lost. Everything that fell in eventually comes back out in the radiation. From Bob's perspective, things look very different. He falls through the event horizon without noticing anything unusual. He enters the interior of the black hole, where the information from the infalling matter is present. He can, in principle, interact with this information inside the black hole. Now, here is the crucial point. Alice and Bob can never compare their observations. Once Bob crosses the event horizon, he can never send a message back to Alice. He cannot tell her what he found inside, and Alice can never enter the black hole to check whether the information is also inside. The two descriptions, Alice's and Bob's, are complementary. They are both valid, but they can never be directly compared, and therefore they never lead to a contradiction. Part 2, but wait, you might say. Does this not mean that the information has been copied? It is both inside and outside. Would that not violate the no-cloning theorem, which says quantum information cannot be duplicated? Susskind's answer was clever. The no-cloning theorem is violated only if someone can actually verify the existence of both copies. If Alice and Bob could meet after the experiment and compare notes, they would find two copies of the same information, and that would be a genuine violation of quantum mechanics. But they cannot meet. Bob is trapped inside the black hole. The no-cloning theorem is only violated if the violation is observable, and in this case, it is not. This is a radical move. It says that physics is observer-dependent in a way that goes far beyond anything in ordinary quantum mechanics or relativity. The very content of reality, what information exists and where it is, depends on who is asking. And different observers may get different answers without any contradiction, as long as they can never compare notes. Complementarity is a beautiful idea, and it had a powerful effect on the field. It offered a way out of the paradox that preserved both quantum mechanics and the broad structure of general relativity at the cost of accepting a new kind of observer dependence in fundamental physics. But complementarity required something even more radical to work. It required that the three-dimensional interior of the black hole could be completely described in terms of physics on the two-dimensional event horizon. All the information inside the black hole had to be encodable on its surface. This idea was already implicit in Bekenstein's entropy formula, which said entropy scales with area rather than volume. But Susskind and Hooft elevated it to a general principle. It is called the holographic principle, and it may be the most profound idea to emerge from the information paradox. The holographic principle, proposed by Gerard et Hooft in 1993 and further developed by Susskind, states that the maximum amount of information that can be contained in any region of space is proportional to the area of the boundary of that region, not its volume. In other words, the physics of a volume of space can be completely encoded on its boundary, much like a hologram, where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image. Think about that for a moment. Everything happening inside a room, every particle, every force, every interaction, all of it could, in principle, be described entirely in terms of information on the walls of that room. The three-dimensional world we experience could be, at the most fundamental level, a projection from a two-dimensional boundary. This sounds insane. It sounds like the plot of a science fiction movie. But as we will see, it has been supported by some of the most rigorous mathematics in theoretical physics. And it all started with the black hole information paradox. The holographic principle resolved a puzzle that had been nagging physicists since Bekenstein's work. Why does black hole entropy scale with area rather than volume? The answer, according to the holographic principle, is that this is not special to black holes. It is a fundamental property of gravity. In any theory that includes gravity, the maximum information content of a region is set by its boundary area, not its volume. Black holes saturate this bound, meaning they pack the maximum amount of information possible into a given region of space. They are the densest information storage devices in the universe. Now, complementarity and the holographic principle were compelling ideas, but they were not proven. They were proposals, frameworks, educated guesses supported by physical intuition and mathematical analogy, but not by rigorous mathematical proof. What the field needed was a concrete realization, an actual mathematical example where holography could be shown to work. That example arrived in 1997, and it changed everything. In 1997, a young Argentine physicist named Juan Maldacena, working at Harvard, published a paper that would become the single most cited paper in the history of high-energy physics. The paper was titled The Large N Limit of Superconformal Field Theories and Supergravity, and its content was nothing short of revolutionary. Maldacena proposed a precise mathematical correspondence between two seemingly unrelated theories. On one side, a theory of gravity, specifically string theory, in a particular type of curved spacetime called anti-de Sitter space. This is a spacetime with a negative cosmological constant, giving it a shape somewhat like the inside of a saddle, with a boundary at infinity. On the other side, a quantum field theory, specifically a supersymmetric gauge theory, living on the boundary of the anti-de Sitter space in one fewer dimension. This correspondence, known as ADS/CFT, states that these two theories are not merely similar, they are exactly equivalent. They are two different descriptions of the same physics. Every process in the gravitational theory, including the formation and evaporation of black holes, has an exact counterpart in the boundary field theory, and vice versa. This was the holographic principle made concrete. A gravitational theory in the interior of spacetime is equivalent to a non-gravitational quantum theory on its boundary. The boundary theory, being a standard quantum field theory, is unitary. Information is preserved. Quantum mechanics works perfectly. And since the interior theory is equivalent to the boundary theory, the interior theory must also be unitary. Information must be preserved there too, even in the presence of black holes. Let me spell out the implication clearly. In the boundary theory, there is no gravity, there are no black holes, there is just quantum mechanics and quantum fields, and unitarity is guaranteed. The boundary theory does not lose information, period. Since the boundary theory is equivalent to the gravitational theory cannot lose information either. Black holes in the gravitational theory must somehow preserve information, even though Hawking's calculation seems to show otherwise. This was an incredibly powerful argument. It did not explain how information escapes from the black hole. It did not identify the flaw in Hawking's calculation. But it provided overwhelming evidence that information is preserved, because the equivalent non-gravitational description guarantees it. The impact of Maldacena's paper was seismic. Within a few years, hundreds of physicists had checked the correspondence from numerous angles, and every check confirmed it. The boundary theory and the gravitational theory agreed on every quantity that could be calculated in both frameworks. The evidence for ADS/CFT grew stronger and stronger. There was an important milestone just before Maldacena's paper. In 1996, Andrew Strominger and Kumrun Vafa used string theory to count the microscopic quantum states of a special class of black holes. Black holes that are both electrically charged and spinning, with certain supersymmetric properties. They counted the states, calculated the entropy by taking the logarithm of the number of states, and got an answer that matched the Bekenstein-Hawking formula exactly, not approximately. Exactly, this was a triumph. It showed that black holes really do have microscopic structure, just like any other thermodynamic system. A box of gas has many microscopic configurations consistent with its macroscopic properties, and that is why it has entropy. Strominger and Waffer showed that a black hole has many microscopic quantum configurations consistent with its macroscopic properties, and that is why it has entropy. The black hole is not a featureless void. It is, at the microscopic level, a fantastically complex quantum system with a well-defined number of quantum states. This result, combined with ADS/CFT, dramatically shifted the consensus in the physics community. By the early 2000s, most physicists were convinced that information is preserved. Hawking's argument, while brilliant, was missing something. The semi-classical calculation was incomplete in some way that allowed information to escape. The shift was so decisive that in 2004, it led to one of the most dramatic moments in the history of physics. In 1997, Stephen Hawking and Kip Thorne had made a public bet with John Preskill of the California Institute of Technology. The terms were clear. Hawking and Thorne bet that information is destroyed in black holes. Preskill bet that information is preserved. The loser would give the winner an encyclopedia from which information could be retrieved at will. In July 2004, at the 17th International Conference on General Relativity and Gravitation in Dublin, Stephen Hawking stood before the assembled physicists and conceded the bet. He announced that he now believed information is preserved, citing arguments related to the ADS-CFT correspondence and a new proposal he had developed regarding how information might escape. He presented Preskill with a baseball encyclopedia, a copy of Total Baseball, the ultimate baseball encyclopedia, from which, as promised, information could be retrieved at will. The moment was extraordinary. The most famous physicist in the world, the man who had created the paradox, was admitting he was wrong. The audience erupted. Photographers snapped pictures. It made headlines around the world. But there were complications. Kip Thorne, who had been on Hawking's side of the bet, refused to concede. He was not convinced by the arguments. And even Preskill, who had won the bet, admitted that he did not fully understand Hawking's new proposal. The specific mechanism by which information escapes remained unclear. Hawking's concession was a landmark cultural moment, but scientifically, it did not resolve the paradox. Knowing that information is preserved is different from understanding how it is preserved. Conceding a bet is not the same as solving a problem. The question remained, what specifically is wrong with Hawking's original calculation? How does information get encoded in the Hawking radiation? What is the mechanism? These questions would drive the field for the next 2 decades. And just when physicists thought they were converging on an answer, a new crisis erupted that was, in some ways, even more severe than the original paradox. Before I tell you about that crisis, I want to introduce you to another crucial figure in our story. His name is Don Page, and his contribution, though it received less public attention than the work of Hawking or Susskind, turned out to be one of the most important of all. Don Page is a Canadian physicist who was Stephen Hawking's graduate student in the 1970s. He worked closely with Hawking, even living in Hawking's home for a period, helping with daily tasks. Page has deep expertise in both general relativity and quantum mechanics, and from very early on, he disagreed with his advisor about information loss. As early as 1980, Page published a paper arguing that information is preserved in black hole evaporation. This was a bold move for a young physicist whose career depended on the support of the most famous scientist alive, his own PhD supervisor. But Page was convinced by the arguments from quantum mechanics. Unitarity was too fundamental to abandon. In 1993, during a Christmas break, Page had an insight that would prove to be critical. He formulated a precise prediction for how the entanglement entropy of Hawking radiation should behave over the course of a black hole's evaporation, if information is indeed preserved. The resulting prediction is called the Page curve, and it turned the philosophical debate about information loss into a quantitative, calculable question. Let me explain the Page curve carefully, because it is central to everything that follows. When a black hole emits Hawking radiation, the black hole and the radiation become entangled. Entanglement is a quantum mechanical phenomenon where two systems are correlated in a way that has no classical analog. The state of one system cannot be fully described independently of the other. They are linked, no matter how far apart they are. Now, there is a way to measure how much entanglement exists between two systems. It is called the entanglement entropy. If you look at just one of the two entangled systems, ignoring the other, the system appears to be in a mixed state, a state of partial uncertainty. The entanglement entropy quantifies this uncertainty. The more entangled the two systems are, the higher the entanglement entropy of each subsystem. Here is what happens during black hole evaporation, according to Page's analysis. At the very beginning, the black hole has just formed and has not yet emitted any radiation. The entanglement entropy of the radiation is 0. As the black hole begins to radiate, each emitted particle is entangled with its partner that fell into the black hole. The radiation's entanglement entropy increases with each successive particle emitted. The entanglement between the radiation and the black hole grows. The entropy of the radiation goes up and up and up. Now, if information is not preserved, if Hawking is right, this entropy just keeps increasing throughout the entire evaporation process. More and more entanglement, more and more entropy, all the way until the black hole is gone. At the end, you are left with a thermal state of maximum entropy. The information is lost. But if information is preserved, something different must happen. Page showed that there is a critical moment, now called the Page time, which occurs roughly when the black hole has emitted about half of its initial entropy. At the Page time, the entanglement entropy reaches a maximum and then begins to decrease. Why does it decrease? Because after the Page time, the radiation that has already been emitted begins to contain enough information to start decoding the black hole. The newly emitted particles are not just entangled with the black hole, they are also correlated with the previously emitted radiation. These correlations are subtle, hidden in complex entanglement patterns among the radiation particles. But they carry information. And as more radiation is emitted, these correlations become stronger. The entanglement between the radiation and the black hole decreases, and the entropy goes down. At the very end of evaporation, the black hole has completely vanished, and the radiation is in a pure state, not a thermal state, a pure state that is incredibly complex, incredibly scrambled, but contains all the information about the original matter that formed the black hole. The entanglement entropy returns to 0. The shape of this curve, rising to a peak and then falling, is the Page curve. It is shaped like an inverted letter V or a mountain peak, and it is the fingerprint of information preservation. If the entropy of Hawking radiation follows the Page curve, information escapes. If it just keeps rising, information is lost. Page had turned the question into something almost experimentally testable, or at least calculationally testable. If you could compute the entanglement entropy of Hawking radiation as a function of time, you could determine once and for all whether information is preserved or destroyed. The problem was that computing this entropy was extraordinarily difficult. The standard tools of semi-classical gravity, the same tools Hawking used, gave an entropy that just kept rising. They could not reproduce the Page curve. To get the Page curve, you would need to include quantum gravitational effects that go beyond the semi-classical approximation. And nobody knew how to do that. For 26 years, the Page curve remained a prediction without a derivation. Physicists believed it was correct, based on arguments from ADS/CFT and general principles of quantum mechanics, but they could not prove it using gravitational calculations. Then, in 2019, everything changed. But before we get to that breakthrough, we need to discuss the crisis that erupted in 2012 and threw the entire field into turmoil. By the early 2010s, most physicists were fairly comfortable with the picture I have described. Information is preserved. Black hole complementarity provides a framework. ADS/CFT gives us confidence. The details would be worked out eventually. There was a feeling that the hardest part was over. That feeling was shattered in the summer of 2012 by a paper that came to be known as the AMPS paper, after its four authors: Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully. Working at the University of California, Santa Barbara, they published an analysis that exposed a deep, previously unnoticed contradiction within the framework of black hole complementarity. The AMPS argument is subtle and involves the quantum mechanical concept of entanglement monogamy, so let me build it up step by step. First, recall what complementarity says. An observer falling into the black hole experiences a smooth, uneventful crossing of the event horizon. Nothing special happens there. This is a prediction of general relativity, specifically the equivalence principle, which says that free fall is locally indistinguishable from floating in empty space. If you are falling into a black hole, your local experience should be identical to drifting in deep space, at least until tidal forces become significant well inside the horizon. For this smooth crossing to work, the quantum state near the horizon must have a very specific structure. Technically, the outgoing mode of the Hawking radiation, the particle that escapes, must be entangled with the corresponding ingoing mode, the particle that falls in. This entanglement between the outgoing and ingoing modes is what makes the horizon smooth and featureless. Without it, the observer falling in would encounter a wall of high-energy particles at the horizon. Second, recall what information preservation requires. After the Page time, the Hawking radiation that has already been emitted is in a highly entangled state, and the newly emitted radiation must be entangled with the earlier radiation. This is necessary for the entanglement entropy to follow the Page curve and eventually decrease. The new radiation must carry information about the black hole's interior, and it does so through entanglement with the old radiation. Now here is the problem. Monogamy of entanglement. Monogamy of entanglement is a fundamental theorem of quantum mechanics that says a quantum system cannot be maximally entangled with two independent systems simultaneously. If particle A is maximally entangled with particle B, then A cannot also be maximally entangled with particle C, where C is a system independent of B. Entanglement is like a resource that must be shared. You cannot give it all to two different partners at once. Apply this to the Hawking radiation. Consider a particle emitted from the black hole after the page time. Call it particle P. For the horizon to be smooth, P must be maximally entangled with its ingoing partner Q, which falls into the black hole. For information to be preserved, P must be maximally entangled with the early radiation R. The particles emitted before the page time. But Q and R are independent systems. One is inside the black hole, the other is far away in space. Monogamy of entanglement says P cannot be maximally entangled with both. Something has to give. AMPS presented 3 options and showed that each one comes with severe costs. Option 1. Give up smooth horizons. If the entanglement between P and Q is broken in favor of the entanglement between P and R, then the horizon is no longer smooth. The breaking of entanglement releases enormous energy, creating what AMPS called a firewall, a surface of high-energy quanta hovering just outside the event horizon. An observer falling into the black hole would not pass through smoothly. They would be incinerated instantly. The equivalence principle, Einstein's most cherished principle, the foundation of general relativity, would be violated in the most dramatic way possible. Option 2. Give up unitarity. If the entanglement between P and R is broken in favor of the entanglement between P and Q, then the horizon remains smooth, but information is lost. We are back to Hawking's original position. Quantum mechanics is wrong. Option 3. Give up the applicability of effective field theory outside the horizon. The description of physics in terms of local quantum fields breaks down even in regions of weak gravity far from the black hole. This would be an even more radical change than the other 2 options. None of these options is palatable. Each one requires abandoning a principle that physicists consider fundamental. And yet, AMPS showed that at least one of them must be wrong. The firewall option was the most discussed and the most disturbing. The idea that falling into a black hole would be lethal not because of the singularity at the center, but because of a wall of fire at the event horizon, was deeply counterintuitive. It contradicted everything general relativity predicted about horizons. It was, as one physicist put it, like discovering that a window you thought was transparent is actually a brick wall. The physics community reacted with a mixture of shock, excitement, and intense debate. Raphael Bousso said something to the effect that a firewall simply cannot appear in empty space, any more than a brick wall can materialize in an empty field. Daniel Harlow called it the most important problem in theoretical physics. Joseph Polchinski, one of the authors, took the argument extremely seriously and spent much of his remaining career grappling with its implications. The firewall crisis showed that complementarity, despite 2 decades of acceptance, was not the final word. It contained hidden contradictions that only revealed themselves when pushed to their logical limits. The information paradox was back, and it was worse than ever. In the years following the AMPS paper, the physics community generated a dizzying array of proposed resolutions. Let me take you through the most important ones. One of the most audacious and beautiful responses came from Juan Maldacena and Leonard Susskind in 2013. They proposed a conjecture that can be expressed in just 5 characters. ER equals EPR. ER stands for Einstein-Rosen, referring to Einstein-Rosen bridges, which are wormholes, tunnels through space-time connecting 2 distant regions. These were first described by Einstein and Nathan Rosen in 1935. EPR stands for Einstein-Podolsky-Rosen, referring to quantum entanglement, the spooky action at a distance that Einstein, Boris Podolsky, and Nathan Rosen described in a famous paper also published in 1935. Maldacena and Susskind's conjecture is that these two phenomena, wormholes and entanglement, are actually the same thing viewed from different perspectives. Every pair of entangled particles is connected by a tiny, Planck-scale wormhole, and every wormhole is a manifestation of entanglement between the quantum degrees of freedom at its two ends. If this is true, it resolves the firewall problem in a beautiful way. The Hawking radiation and the black hole interior are connected by a network of wormholes. They are not truly independent systems. And if they are not independent, the monogamy argument does not apply. The outgoing particle can be entangled with both its ingoing partner and the early radiation, because those two systems are actually connected through the wormhole network. The ER equals EPR proposal is breathtaking in its scope. It suggests that the geometry of spacetime itself is woven from quantum entanglement. Where there is entanglement, there is a connection in spacetime. Where there is no entanglement, spacetime falls apart. Space is not fundamental. It emerges from the patterns of quantum entanglement among the fundamental degrees of freedom of the universe. This idea has deep connections to other developments in theoretical physics, particularly to the concept of emergent spacetime. The idea that the smooth, continuous spacetime we experience is not a fundamental ingredient of nature, but rather an approximate, large-scale description that emerges from some deeper quantum substrate. Much as the smooth surface of a lake emerges from the chaotic motions of trillions of water molecules. The ER equals EPR proposal remains a conjecture. It has not been proven in the mathematical sense. But it has inspired a vast amount of research and has profoundly influenced how physicists think about the relationship between spacetime and quantum mechanics. Another important response to the firewall crisis came from Samir Mathur and the fuzzball program, which was actually developed before the AMPS paper but gained renewed attention afterward. Mathur, working in the framework of string theory, proposed that black holes are not the way general relativity describes them at all. There is no smooth event horizon. There is no empty interior. There is no singularity. Instead, the entire structure, from what would have been the horizon to what would have been the singularity, is filled with a complex, tangled web of strings and higher dimensional objects called branes. The whole thing is a fuzzball, a quantum object with detailed microscopic structure extending all the way to the horizon scale. In the fuzzball picture, when matter falls toward a black hole, it does not cross a smooth horizon into an empty interior. Instead, it interacts with the complex, stringy structure at the surface and gets absorbed into it. The information is encoded in the detailed configuration of the fuzzball. When the fuzzball radiates, the radiation carries information about the fuzzball's state, just as radiation from a burning piece of coal carries information about the coal. There is no information loss, no paradox, no firewall. Mathur and his collaborators have constructed explicit fuzzball solutions in string theory for certain classes of black holes, particularly extremal and near-extremal black holes. These solutions are called microstate geometries, and they are genuine solutions of the string theory equations that have the same mass, charge, and spin as the corresponding black hole but differ from it in their internal structure. Each microstate geometry represents a different microscopic configuration, a different arrangement of the strings and branes, and the total number of such configurations matches the Bekenstein-Hawking entropy. The fuzzball proposal is attractive because it completely eliminates the information paradox. There is no horizon in the traditional sense, so there is no issue with information getting trapped behind it. The information is always accessible, encoded in the surface structure of the fuzzball. However, the fuzzball program faces significant challenges. The explicit microstate geometries have been constructed mainly for special black holes with high degrees of symmetry, and it is not clear how to extend them to more generic, astrophysically relevant black holes, like the Schwarzschild black hole formed by a collapsing star. There are also questions about what it would feel like to fall into a fuzzball. Would you notice anything different from falling into a classical black hole? The answers are not yet clear. Another proposal came from Stephen Hawking himself, in collaboration with Malcolm Perry and Andrew Strominger. In 2016, they published a paper titled "Soft Hair on Black Holes." This paper proposed that the no-hair theorem, the idea that black holes are completely characterized by mass, charge, and spin, is not exactly correct. Hawking, Perry, and Strominger argued that black holes carry additional information in the form of soft hair, which consists of zero-energy or ultra-low-energy particles, soft photons and soft gravitons, that live on the event horizon. These soft particles are produced whenever anything crosses the horizon, and they record a kind of imprint of what went in. The soft hair is invisible to the standard no-hair theorems, because those theorems only consider finite energy excitations. The zero-energy soft particles slip through the cracks of the traditional analysis. This was one of Hawking's final scientific contributions. He passed away on March 14, 2018, at the age of 76, and his posthumous paper on soft hair was published later that year. The proposal is interesting and has stimulated significant research, but most physicists believe that soft hair alone is not sufficient to fully resolve the information paradox. It may account for some of the missing information, but the detailed mechanism by which all the information escapes in the Hawking radiation remains unclear. There were also proposals from the community working on loop quantum gravity, an alternative approach to quantum gravity that does not rely on string theory. In loop quantum gravity, space-time has a discrete, granular structure at the Planck scale. Black holes in this framework can have a very different fate than in classical general relativity. Instead of ending in a singularity, the collapsing matter may bounce, creating a new expanding region on the other side. This could lead to scenarios where information is preserved, either by escaping during the bounce or by being stored in a long-lived remnant. The remnant idea proposes that a black hole does not evaporate completely. Instead, when it reaches a tiny size, comparable to the Planck mass, the evaporation stops, leaving behind a stable or very long-lived remnant. This remnant, though tiny, retains all the information that fell into the original black hole. The remnant could have an enormous number of internal states, enough to store all the information. Eventually, the remnant might decay very slowly, releasing the information over an extraordinarily long timescale. Remnant proposals face their own challenges. If remnants can store arbitrarily large amounts of information in a Planck-sized package, this leads to a potentially infinite number of species of Planck mass particles, which can cause problems with the consistency of quantum field theory. These issues have been debated extensively, and there is no consensus on whether they are fatal to the remnant idea or merely technical difficulties that can be overcome. So by the mid-2010s, the landscape of proposed solutions was vast and varied. Complementarity, holography, fuzzballs, firewalls, ER equals EPAR, soft hair, remnants, each had its strengths and weaknesses. Each addressed some aspects of the paradox while leaving others unresolved. The field was rich with ideas, but lacking a definitive answer. What physicists desperately needed was not another clever proposal, but a concrete calculation. Specifically, they needed to compute the entanglement entropy of Hawking radiation as a function of time and determine whether it follows the Page curve. If they could do that, using gravitational methods, it would constitute strong evidence that information is preserved, independent of any specific proposal about the mechanism. And in 2019, that calculation was finally achieved. This is the part of the story where I need you to pay very close attention. Because what happened in 2019 is, in my opinion, the most exciting development in this entire 50-year saga. Two groups of physicists, working largely independently, published papers that computed the entanglement entropy of Hawking radiation and showed that it follows the Page curve. The papers were by Jeffrey Pennington of Stanford and Berkeley, and by Ahmed Almheri, Netta Engelhardt, Donald Marolf, and Henry Maxfield. Let me explain what they did and why it is so remarkable. The key tool was a formula for computing entanglement entropy in gravitational systems. This formula had its roots in the work of Shinsei Ryu and Tadashi Takayanagi, who in 2006 proposed a beautiful formula for calculating entanglement entropy in the context of ADS/CFT. The Ryu-Takayanagi formula says that the entanglement entropy of a region in the boundary theory is given by the area of a minimal surface in the bulk gravitational theory that is anchored to the boundary of that region, divided by 4 times Newton's constant. This is a stunning connection between geometry and quantum information. The entanglement entropy, a purely quantum concept, is calculated by finding a geometric surface, a purely gravitational concept. It is holography at work, with geometry encoding quantum information. The Ryu-Takayanagi formula was originally developed for static spacetimes, but it was later generalized to dynamical situations by various researchers, including Engelhardt and Wall, who proposed the quantum extremal surface formula. This generalization includes not only the area of the surface, but also the entropy of quantum fields in the bulk, and it applies to time-dependent processes like black hole evaporation. The quantum extremal surface prescription says the following. To calculate the entanglement entropy of the Hawking radiation, you need to find a surface in the gravitational spacetime that is extremal, meaning it is a saddle point of a certain functional that includes both the geometric area and the bulk quantum entropy. The entanglement entropy of the radiation is then given by this functional evaluated at the extremal surface, with the prescription that if there are multiple extremal surfaces, you pick the one that gives the minimum entropy. Now, when Pennington and Almheri and collaborators applied this prescription to an evaporating black hole, they found something remarkable. At early times during the first half of the evaporation, there is only one extremal surface, and it gives an entropy that increases with time. This matches Hawking's calculation. So far, nothing new. But at late times, after the Page time, a new extremal surface appears. This new surface lies inside the black hole, near the singularity, and it bounds a region that the researchers called an island. When this new surface is included in the calculation and the minimum prescription is applied, the entropy begins to decrease. The entanglement entropy follows the Page curve.